for large data center customers and cloud providers. And so we're trying to solve their specific issues, if you want to say. And one of the things we're working on together with others in IETF is a new protocol for the data center, which is called routing in fat trees, or in short, Rift. So very briefly on the agenda, I want to start with why are we working on this new protocol? What issues are we seeing and trying to solve? Then we'll go into what is Rift, what some of the basic concepts. We'll touch on some of the advantages. And I have a very brief update on where we are in IETF currently, and can mention some implementations. Why do we need a new protocol in IP Fabric or in the data center? If you look at what is happening in the data center, there's a few interesting trends going on, and some of them were already mentioned in one of the previous presentations. Bandwidth consumption is massively growing. A lot of our customers, what I'm seeing is that they are pushing even more traffic within the data center than outside of the data center. In some cases, even up to 80% of traffic is inside the data center. And so although a lot of enterprises especially are moving into cloud, you can imagine that, well, cloud is just someone else's computer in a data center. The bandwidth needs within the data center are exploding, if you want to say. Especially if you focus on hyperscalers and very large data centers, you see that they don't just use IP fabrics within the data center for server farms, but the trend going on now is to move away from big chassis to what we call scale-out architecture. So even in Metro and the WAN, we see that routers are now being built in a disaggregated or a distributed fashion. So in other words, we see customers building, for example, peering routers with 1U boxes connected to an IP fabric. And so the driver, one of the biggest drivers behind that is that a lot of these large data centers and hyperscalers are more interested in specific features of a chipset than that they're interested in proprietary or so they're looking for a how do you say that, generic box or chipset they can use within their data center, sort of independent of who builds the box around it. So a lot of these customers are looking into features, but also if you do, for example, power calculations, if you put a big chassis in your data center and you don't use the full capacity, you can imagine that it's not that power efficient, right? Because the power supplies are built to power the whole chassis, but if you only put in like 2 or 3 line cards where you could put in 16, you're using much more power than you could. So a lot of these data centers are looking into building scale out instead of scale up. Some other trends we're seeing is L3 forwarding is the new L2. So we're sort of preaching and now seeing that we want to get rid of L2 wherever possible. So especially in DCI, data center interconnect, you would not want to run L2 because of all the typical L2 issues as DCI. So a lot of these networks are still using link state protocols. And they have advantages, right? So one of the biggest advantages is that conversion is really fast. There's probably, well, not much protocols that can do conversion faster. The problem is that each node sort of has its own version, its own view of the whole network, the whole topology. And that does work pretty well in a small scale. However, if you imagine a hyperscaler having a data center with a few thousand switches, that can become a problem. Not only because you need, for example, large FIP scale or RIP scale, but also because of the fluting, right? If something changes within the network, every node needs to get that update. And because of all those updates being sent around, in majority of cases, the newest version of an update wins, which could be handy, but not always if you want to do, for example, load balancing within the network. Yeah, so and then the other alternative, if you want to say, is a distance or path vector protocol, where you see some of the issues, the prefixes being advertised around the network. Every node within the network needs to calculate a best path and re-advertises that route or path to other nodes. So it's also called routing by rumor. You can imagine that's at least slower compared to a link state protocol routing. And there's a lot of other issues like loop prevention. If you run iBGP or eBGP, you need allow AS in, or it's really easy to create loops. So that's not ideal as well. So what we've did as an industry over the past few years is we sort of created a lot of bandages, and especially if you look at the larger DC fabrics, they basically all use eBGP as a de facto for IGP. But as mentioned, it's really easy to create loops, allow AS in, allow own AS in. Sorry. We've introduced tweaks like add path. But again, if you build a very large fabric, you run out of private ASNs. And so there's a lot of sort of ways to, or bandages we put around it. And on the other hand, we see customers running ISIS, for example, as well as with BGP bandages to sort of tweak ISIS to be able to build your IP fabric underlay. The problem with ISIS is that, and that is solved in different work in IETF as well, but that in general, there's a lot of overhead from the protocol itself. So what are the requirements? This is maybe not a full, complete overview, but it sort of shows the differences between what does BGP solve or cannot solve, what does ISIS solve or cannot solve, and on the right side, some of the advantages of this new protocol, Rift. You see on the left side a lot of issues that are sort of being taken care of by modifying BGP or ISIS. But with Rift, it sort of started from the other way around. So first, they came up with a list of issues they wanted to solve and then build a protocol around it instead of the other way around. And you see there's advantages and disadvantages also for Rift. It is maybe not the simplest to implement initially, because it's of course a learning curve. New protocol works different than what we're used to, and we'll get to how it actually works. So how does it work? Basically, if you break it down, it comes down to that it's a link state protocol northbound and a distance vector protocol southbound. So what does that mean? If you look at from the bottom of the fabric, so the level 0 in this case, those boxes that could be switches or servers connected to the fabric, they only have default routes northbound. So they have no knowledge at all about the rest of the network. And the good thing is, and the reason for doing that is that you can use really cheap silicon for those boxes. And so the other way around, if you look at the green and the red boxes in this picture, they know only the routes which are southbound of them, right? So even the green boxes, they know the more specific routes of the blue boxes, but up they only see a default route. And so this scales very well. Here you see just 3 levels, but this would scale up to 5 or maybe even 7 layers if needed. Where if you would have a link failure or node failure, we'll get to that in one of the later slides, the protocol automatically disaggregates prefixes. So that is one thing that is, and you only need to disaggregate, and that's interesting, 1 level up. So even a disaggregated prefix doesn't have to be known by the whole fabric. So let's zoom into some of the other advantages and to continue on the disaggregation. So in this picture, again, we have a 3-level fabric where P1 on the right side downside of the picture is connected to the gray boxes. Then they are connected to the green boxes A and B, and the top of the fabric is red A and B. And you see that B is missing links towards the green boxes. So now imagine that if you're connected to the left side of this fabric, and B would still originate a default route down in the fabric, then B would obviously black hole traffic for P1. So what happens is that as soon as Rift detects that one of the links is missing or a box goes missing, it'll inject a more specific into the fabric. So in other words, a P1 is now advertised by alpha as a more specific. And so it'll automatically will attract the traffic for P1. And so another thing which is quite unique for Rift is that it can do unequal path load balancing. And so we solve the problem of having links of different speeds within the fabric. I won't go into the whole algorithm behind it, but you sort of get an idea from the picture here. Another thing which is interesting in Rift is that it has the capability to detect miscabling. So in other words, Rift uses what we call zero-touch provisioning. That's due to that the underlay runs on v6, so using neighbor discovery, that's the foundation of CTP. But it also detects, for example, if switches within one level are not interconnected with each other. And so it can automatically detect those link failures. Another good thing of CTP is that you only need to provision or have to provision the top of the fabric. So all the configuration is done at the top of the fabric. And because of CTP, it detects that nodes are connected and in which layer they are. So another thing is it's an open standard. It's currently being worked on in the Rift working group in IETF. The main contributors are Juniper and Cisco. There are some other interested operators helping out as well. And the latest version, which is revision 11, if I'm correct, is about to go for work with Lost Call. So we're getting to a standard there. Again, one of the other advantages, it can operate on asymmetric bandwidth fabrics, detects link failures, and will inject more specifics to work around that. It scales very well multi-level, where if you look at, for example, BGP or ISIS, you will run into scaling issues, especially with the very deep fabrics, 5 or maybe even 7 layers layers deep. So multi-homing servers is something that can easily be done in Rift. For example, if you run a routing stack on the host, it can directly become part of the fabric. And so you can provision whatever overlay tunnels you want to use. So BFD is not, as with BGP and ISIS, an extra protocol you need to run, but a fast rehash and early loss detection is built in Rift, if you want to say. Another thing which is really interesting, it's a minimal blast radius. Again, failures are have to be detected only one level up. As what we just saw, that's the position where you need to inject your more specific in case of a node or link failure. Flooding is around 30% reduction if you compare to ISIS. So that definitely in high traffic and fabrics with lots of nodes, up to thousands of nodes, that really makes a difference. It is by design loop free. So as what we've just seen, Rift will try to utilize all links available as long as they are not detected as miscabling. And let me see. Yeah, so coming back to the standardization, I already touched briefly on that. It's being worked on in IETF in the Rift working group. Co-authors from Cisco, Yandex, Mellanox, and others are working on it. And there are some sort of implementations, either in beta or early releases. There is a package for Junos, which you can install if you run 19.4 R1 or newer. You can download the package, install it, and run Rift. It is also in some of the virtualized or containerized Junos releases. And there's an open source implementation written in Python by Bruno Reisman. And so Bruno and Juniper have done a lot of IO testing as well to make sure that the protocol is built both by Juniper and by Bruno according to what is written in the Rift draft. And so that is it. I'm not sure if I can hear or read any of the questions. Let me quickly go to the chat. Ellen, I'm not sure if there are questions, because I cannot hear you, so maybe you can type them.
So we have a little bit of a sound problem here with this.
So no questions. If there's any questions afterwards, if you want to test Rift, feel free to reach out. I'm based in the Netherlands, but my region is EMEA, so I'm happy to help out. Just drop me an email, melchior@juniper.net. And yeah, let's play around with it. Thanks.
Thank you, Melchior.